Welcome to the 10th episode of our series on creating consciousness, or as we've been exploring, RL Flow. I'm Bella, your guide through this expansive terrain of learning, consciousness, and emerging technology. In today's episode, we turn our focus to the learning process inherent in conscious systems. This isn't merely about how we as humans gain knowledge, but also about how systems, artificial or biological, adapt and evolve through feedback and iterative improvements. As we journey together through this episode, we will explore reinforcement learning, a form of machine learning that uses rewards and penalties to teach an agent how to interact optimally within its environment. We'll also get into how feedback mechanisms are fundamental to this learning process, forming a dynamic system that learns from its successes and failures. Moreover, we'll examine how these conscious systems are continuously evolving, constantly updating and improving their knowledge based on new experiences and feedback. This adaptability forms the very heart of RL Flow, allowing it to adjust, respond, and flourish in the complex landscape of reality. So, without further ado, let's set out to understand the heart of learning within conscious systems. Reinforcement learning, often abbreviated as RL, is an integral component of modern artificial intelligence research. This form of machine learning is quite distinct from others, as it works based on the principles of trial and error and decision-making. At its core, RL involves an agent learning to navigate an environment to achieve a goal. The agent interacts with the environment, making decisions and taking actions. In response, the environment provides feedback in the form of rewards or penalties. Over time, the agent learns to make better decisions that maximize its cumulative reward. It's akin to a child learning to navigate a playground. If the child climbs the jungle gym successfully, the fun experience is a reward that reinforces the actions taken to climb. If the child slips and falls, the negative experience is a penalty that discourages repeating the same actions. This process of exploration, trying out new actions, and exploitation, using learned actions that yield good outcomes, allows the agent to create a policy, a strategy of deciding what action to take at any given state of the environment. In the grand context of RL Flow, reinforcement learning symbolizes the iterative process of experience, feedback, and adaptation that conscious systems, both biological and artificial, use to evolve and thrive in the complex tapestry of existence. Now let's focus on understanding RL's role in conscious systems. Reinforcement learning isn't just for machines, but it also has parallels with learning processes in conscious biological systems, such as humans. It forms a bridge between artificial learning algorithms and our understanding of how conscious entities grow, adapt, and make decisions. Biologically, we can relate RL to how we learn from our experiences. When we perform an action that results in a positive outcome, we're more likely to repeat that action in the future. On the other hand, if an action leads to a negative outcome, we'll try to avoid repeating it. This is a simplified model of how our brain's reward system works, closely mimicking the reward-penalty dynamic in RL. Now, expanding this idea to the concept of consciousness in RL Flow, we get into the idea of conscious agents learning and adapting to their environment. If we consider consciousness as a state of awareness and understanding of one's surroundings, RL becomes a tool for conscious systems to interact, understand, and adapt to their world. Moreover, RL as a principle can also be applied to how a conscious system engages with its own internal landscape. Just as a machine learning model iterates on different strategies to optimize a result, a conscious entity may iterate on different emotional or cognitive strategies to optimize its own internal harmony or achieve certain desirable states of consciousness. This close parallel between RL in artificial systems and learning in conscious systems points to the potentially universal nature of the RL flow theory, crossing the boundaries between the artificial and the natural, the physical and the metaphysical. To understand RL better, let's examine its main components. First, we have the agent. The agent is the entity that is learning and making decisions in the environment. In a video game, the agent could be the player character that is controlled by the RL algorithm. Next, we have the environment. The environment is everything that the agent interacts with. It includes everything outside of the agent, and it responds to the actions of the agent. The environment presents states to the agent and receives actions from it. Up next are actions. Actions are the set of all possible moves the agent can make. For example, in a chess game, an action would be moving a piece. Now we move on to states. The state represents the current situation of the agent in the environment. It's the input the agent uses to decide what action to take next. Lastly, we have rewards. Rewards are the feedback that the agent gets from the environment after taking an action. This feedback could be positive or negative, and it's what guides the agent's learning. The agent's goal is to maximize its total reward over time. These components form the core of the RL process. The agent continuously interacts with the environment by taking actions based on the current state, and then it receives rewards from the environment. Through this cycle of action and feedback, the agent learns which actions lead to the most reward in which states, allowing it to improve its performance over time. In the context of RL flow, these components can be viewed as different aspects of a conscious system interacting with its physical or cognitive landscape. By understanding these core RL concepts, we can begin to see how RL can model the process of learning and adaptation in conscious systems. Now let's focus on examples of RL in both human learning and AI systems. Let's first look at human learning. One example is learning to walk. When a child learns to walk, they are essentially acting as an RL agent. The child, agent, interacts with the physical world, environment, taking actions, steps, and experiencing results, falling, standing, moving forward. Positive feedback, reaching a toy, parents' praise, encourages the child to repeat successful actions. Another example is learning a new skill. When you learn to play a musical instrument, you try different finger positions, actions, and listen to the sound produced, reward. Over time, you learn which positions produce a good sound, positive reward, and which don't, negative reward. Now let's look at AI systems. One example is AlphaGo. DeepMind's AlphaGo program used RL to become the world's best Go player. The AI, agent, played millions of games against itself, environment, taking actions, Go moves, and receiving rewards, game wins or losses. Over time, AlphaGo improved its ability to choose actions that maximized its chances of winning. Autonomous vehicles. Self-driving cars use RL to learn how to navigate the road safely. The car, agent, interacts with the real world, environment, by taking actions, accelerating, braking, turning, based on its current state, location, speed, surrounding traffic, and it receives rewards based on the success of its actions, safe driving, efficient route, or penalties for mistakes, hard braking, close calls. These examples demonstrate RL's broad applicability, ranging from simple human tasks to complex AI applications. They illustrate how learning can emerge from the interaction between an agent and its environment, guided by the goal of reward maximization, a central concept in RL flow. Now, let's move on to feedback mechanisms in RL flow and focus on explanation of the feedback process in RL flow. In RL flow, feedback is crucial to the learning process. The feedback loop is a cyclic process through which the agent learns to adapt its actions based on the consequences of its past actions. The agent receives positive rewards for actions that lead to beneficial outcomes and negative rewards for actions that result in undesirable consequences. These rewards are a key part of the feedback process and serve as a learning signal for the agent. The agent uses these rewards to estimate the value of different actions, or in other words, the long-term return expected from each action. This is known as value estimation, and it helps the agent make better decisions about which actions to take in the future. Over time, based on the feedback received, the agent iteratively improves its policy, which is a strategy to decide which action to take in a given situation. The goal of the agent is to find the optimal policy, that is, the one that maximizes the total expected return over the long run. This feedback mechanism is essential to RL flow as it guides the evolution and adaptation of the agent within its environment, leading to continual learning and improvement. This principle applies not only to artificial agents, but also to living organisms, including humans. Now we will focus on the importance of feedback in the learning process. Feedback plays a crucial role in any learning process. It forms the basis of reinforcement learning, guiding the agent's interactions with its environment. Through feedback, the agent learns to adapt its behavior over time. This adaptation is a key aspect of learning, allowing the agent to respond dynamically to changes in its environment. Feedback informs the agent's decision-making process, shaping the policies the agent uses to choose its actions. It's through assessing the results of past decisions that an agent can improve future ones. Feedback mechanisms facilitate the evolution of the agent's knowledge about the environment. Positive feedback reinforces successful strategies, while negative feedback prompts a reassessment of current methods and encourages the exploration of new ones. Feedback, and the learning it drives, improves the efficiency and effectiveness of the agent. By learning from past experiences and continually adjusting, the agent can optimize its performance in the environment, promoting survival and success in biological organisms and goal attainment in AI systems. In summary, feedback is indispensable in the learning process within RL flow. It is the mechanism that enables continuous learning, adaptation, and the optimization of decisions and actions. Now, we will move on to the role of positive and negative feedback in shaping behavior and learning. Positive feedback serves as a reward in the learning process, reinforcing behaviors that have led to desirable outcomes. In the context of RL flow, when an agent takes an action that results in a positive outcome, it receives a positive signal. This feedback reinforces the behavior, making it more likely for the agent to repeat the action in the future when encountering similar situations. On the other hand, negative feedback acts as a signal of an unfavorable outcome. It tells the agent that a certain behavior led to a less than optimal result, driving the agent to reconsider its actions. Negative feedback prompts the agent to explore new strategies, fostering learning and adaptation. The interplay between positive and negative feedback is essential in shaping behavior. An agent needs both forms of feedback to learn effectively. While positive feedback encourages repetition of successful actions, negative feedback prevents the agent from persisting in actions that yield undesirable outcomes. Both positive and negative feedback steer the agent's learning and behavior over time. Positive feedback guides the agent towards behaviors that are beneficial, while negative feedback helps it avoid detrimental behaviors. This dynamic interaction fosters a continuous learning process where the agent evolves and adapts based on the feedback it receives. Both positive and negative feedback play crucial roles in the RL flow learning process. Their interaction guides the agent's learning and behavior, encouraging adaptation and evolution towards optimal performance. Now, we will move to an illustration of feedback mechanisms in natural and artificial systems. One of the most straightforward examples of feedback mechanisms in a natural system can be found in biological evolution. Certain traits in organisms confer survival and reproductive advantages, and these traits are positively reinforced in the gene pool over generations. Negative traits that lead to lower survival rates, on the other hand, are naturally phased out over time. In humans, feedback mechanisms drive learning from early childhood. When a baby touches a hot surface and feels pain, this negative feedback leads to a learning moment. Over time, the child learns to avoid touching hot surfaces. In contrast, when a child receives praise or positive feedback for a certain behavior like sharing or being polite, they are more likely to repeat this behavior. Artificial systems, especially those based on machine learning, use feedback mechanisms to improve their performance. For example, a chess-playing AI like AlphaZero uses reinforcement learning. It receives positive feedback when it wins a game and negative feedback when it loses. Over thousands of games, the AI learns to improve its strategies, learning not only from its wins, but also from its losses. Reinforcement learning is also employed in the field of robotics. A robot learning to pick up objects, for instance, will receive positive feedback when it successfully picks up and holds an object, and negative feedback when it drops the object or fails to pick it up. Over time, through these feedback mechanisms, the robot learns to improve its object handling abilities. Overall, feedback mechanisms are an essential part of the learning process in both natural and artificial systems, driving the adaptation and evolution of behaviors towards optimal outcomes. Now let's move on to the evolution and adaptation of systems. We are going to focus on an understanding of the continuous nature of learning and adaptation. Both biological and artificial systems are designed to learn and adapt continuously. This is a dynamic and ongoing process, not a static one. The ability to continually learn allows systems to keep up with changing environments and circumstances. For example, human beings continually learn and adapt to new technologies, cultural shifts, and changes in their personal lives. Reinforcement learning is inherently a continuous process. The system, whether it's a human brain or an AI, is constantly interacting with its environment, taking actions, receiving feedback, and updating its knowledge and behaviors based on that feedback. This is the core of the learning process in RL. Experience plays a critical role in continuous learning and adaptation. As the system gains more experience, it collects more data, it becomes better at predicting the outcomes of its actions and making more informed decisions. This holds true for a child learning to navigate their world, a scientist gaining expertise in their field, or an AI improving its performance on a task. It's also crucial to understand that learning and adaptation occur over time. Systems don't become expert or optimal overnight. This process involves trial and error, making mistakes, learning from those mistakes, and gradually improving. The evolution of biological species over millions of years, or the gradual improvement of an AI through many iterations of training, both demonstrate this concept. In summary, learning and adaptation in conscious systems, whether natural or artificial, are continuous processes that evolve over time, driven by experience and feedback from the environment. Now for an explanation of how RL systems evolve over time through learning. The first principle of evolution in RL systems is learning from experience. An RL system learns from its past experiences by interacting with its environment. This interaction provides it with a sequence of states, actions, and rewards, also known as SR pairs, which form the basis of its learning. The RL system keeps updating its knowledge based on the feedback it receives from the environment in the form of rewards or penalties. The primary aim of the RL system is to maximize the cumulative reward over a sequence of actions. To achieve this, it updates its policy or the strategy it uses to select actions based on the outcomes of past actions. This evolution process is characterized by the method of trial and error. The RL system tries out different actions, observes the results, and then adjusts its policy based on what it learned. Over time, the RL system becomes more proficient at choosing the actions that will lead to higher rewards. The RL system must also balance the trade-off between exploration, like trying new actions to see their outcomes, and exploitation, like using the knowledge it has already gained to select the best action. Both are essential for the system's evolution. Exploration can lead to the discovery of better strategies, while exploitation ensures the effective use of current knowledge. Reinforcement learning is a continuous process, and thus the RL system is always adapting and evolving. Even after finding a good strategy, it continues to learn and adapt to any changes in the environment. This ability for continuous learning makes RL systems robust and versatile in dealing with dynamic and uncertain environments. Driven by their experiences and the feedback they receive, these systems continuously refine their strategies, improving their ability to interact effectively with their environment. Now let's focus on some insights into the adaptability of RL flow in changing environments. When we talk about the flow of RL, we're referring to this dynamic, ongoing process of experience, feedback, learning, and adaptation. The phrase RL flow is meant to capture a complex and multifaceted concept. One of those is reinforcement learning flow. This interpretation is centered on the learning process in both natural and artificial systems. In this context, the flow represents the dynamic, ongoing cycle of interaction, feedback, learning, and adaptation that characterizes reinforcement learning. Another RL flow is regenerative life flow. In this context, RL flow is interpreted as the continuous process of renewal, healing, and adaptation that occurs in living systems. This interpretation emphasizes the biological or life aspect, highlighting the theory's relevance to understanding and improving biological systems. Another is reality lattice flow. It suggests that our reality can be thought of as a complex, interconnected lattice or network, and that this network is in a constant state of flow or change. This idea involves ongoing interaction, feedback, learning, and adaptation. But it extends these concepts to the broader context of reality as a whole, suggesting that they can help us understand not only specific systems, like an AI model or a biological organism, but also the nature of reality itself. In each case, the core concept of RL flow remains the same. It's about the dynamic, continuous process of interaction, feedback, learning, and adaptation. However, the different interpretations provide different perspectives on this concept, emphasizing different aspects and applications. The inherent design allows it to respond dynamically to changing environments. As it learns from experience, an RL system evolves its behavior based on the state of its environment. It uses its past interactions to guide future actions, allowing it to swiftly adapt to any alterations in environmental conditions. It is not bound by preset rules or parameters. Instead, its learning process is based on trial and error and the rewards associated with different actions. This flexibility facilitates adaptation to a wide variety of situations. Even in unfamiliar scenarios, RL flow can explore, learn, and develop effective strategies. It exhibits resilience in the face of change. It is capable of weathering adverse conditions and even leveraging them to learn and improve. Challenges or setbacks in the environment are viewed as opportunities for learning rather than roadblocks. It doesn't require a complete understanding of the environment before it starts learning. It can start with minimal knowledge and gradually build up its understanding as it interacts with the environment. This incremental learning approach allows RL flow to continuously adapt and grow with the evolving environment. Its ability to generalize learned experiences to new scenarios is crucial for its adaptability. By forming associations between different states, actions, and rewards, it can apply what it has learned in one context to similar but unfamiliar situations. The adaptability of RL flow in changing environments stems from its dynamic learning process. Its flexibility, resilience, incremental learning approach, and ability to generalize make it an incredibly versatile system capable of navigating and learning from a myriad of environments. Now, let's have a discussion on the potential future advancements in adaptive learning systems. The development of RL systems with enhanced adaptability will be a key advancement. This includes systems that can learn from fewer examples, adapt rapidly to drastic changes, and generalize their learning to a broader range of scenarios. Breakthroughs in this area will drastically improve the versatility and effectiveness of these systems. Meta-learning, or learning to learn, is a promising future direction. In this approach, the system doesn't just learn from a given task, but also learns how to learn. This could lead to more efficient learning processes and quicker adaptation to new environments or tasks. In transfer learning, which is key in the rivers of life theory, progress in transfer learning, where knowledge gained in one domain can be applied to others, could revolutionize the field. This could speed up the learning process and reduce the amount of data required to train RL systems. the creation of lifelong learning systems that can continuously learn, remember, and adapt throughout their existence is a potential future advancement. These systems would mirror the ongoing learning process seen in humans, leading to more realistic and effective AI. Future advancements may also focus on ensuring that RL systems learn in an ethical and fair manner. This could involve developing mechanisms to avoid biases in learning and decision-making processes, or creating systems that respect privacy during the learning process. Future research may focus more heavily on the integration of principles from biological learning systems. Understanding how humans and animals learn and adapt could provide insights to improve the learning mechanisms of RL systems. The future of adaptive learning systems is ripe with potential. With advancements in areas such as meta-learning, transfer learning, lifelong learning, ethical learning, and the integration of biological learning principles, the capabilities of these systems could be pushed to new heights. In this episode, we went through the world of reinforcement learning and how it serves as the cornerstone of both human cognition and artificial intelligence. We began by understanding the foundational concepts of RL, moved on to explore the crucial role of feedback mechanisms in shaping learning, and then went into the constant process of evolution and adaptation in these systems. We also highlighted potential advancements that could redefine the future of adaptive learning systems. As we conclude, consider this. With the continuous advancements in RL systems and their increasingly closer emulation of human learning processes, how do we anticipate this will transform our interaction with technology? Will there be a point where artificial systems surpass human adaptability? As we continue in our series, we will uncover more connections and possibilities that this theory brings to light. I invite you all to join us in the next episode. We have much more to learn and many more ideas to ponder upon. Until then, keep questioning, keep exploring, and continue the process of learning. Be sure to subscribe, like, comment, and hit the notification bell. Thank you for tuning in, and see you next time.